So what I want to do this morning is give you, as the title says, an introduction to probabilistic models and more or less ease you into the topic. So I'm going to start more or less from a more knowledge-based perspective and with a focus on interpretability before going more into the learning part, just to show you that there are actually connections there. And you also all have very different backgrounds, probably, so I also hope that at the end of this morning you more or less are evened out with the knowledge you have. And anytime you have any questions, please feel free to ask. And let's see how it goes. Okay, so if we think about AI, then probably chess is one of the things that people have been working on from the beginning, with the idea that that is something that is hard for humans. So it must, of course, also be hard for AI. And if you have a program that can play chess, then it must be intelligent. The big successes in chess are already from halfway through the 90s. When, of course, Kasparov was in the end beat by Deep Blue. But that didn't really make much of an impression, at least maybe in the AI community, but not in the rest of the world. And what we've seen recently is that AI, think about ChatGPT, for example, is impressing everyone outside of the community and the general public. So this is also something that the quote up here was from an interview from the BBC with Peter Heine Nielsen, who's the chess grandmaster and also the coach of Magnus Carlsen. He says, "I always wondered how it would be if a superior species landed on Earth and showed us how they play chess. Now I know." And then I wonder, okay, what do you know? Because this is about AlphaZero learning chess in 4 hours and then being really good at it. Is it showing us how to play chess, really? Right? We may be baffled, perhaps, that it managed to learn something, and we may check that it correctly plays chess, but does it really show us how to play chess? So we've got this system really good at chess, but do we understand it? Do we understand what it's doing? Right? Are we able to interpret the model that is underlying it? And that is one of the things when we think about probabilistic modeling, rather than all those black box machine learning systems, we try to make models that are interpretable, that we have a feeling that we really know what it's doing. So that is going to be the main reason for looking at probabilistic models. We want to have a grip on what they're doing so that we can understand and explain what's going on. And for some applications that may not be very important, right? For chess, it's if you have a system that plays chess and you can see that it abides by the rules, and even if it doesn't, as long as you have fun playing against it, right? It's not that important. But if you think of other applications in law and in medicine, where you really have to be able to rely on what the system is doing and trust any advice or whatever, then it is really important that you understand what is going on. Okay, so to just give you some examples of systems, probabilistic systems, where it also is important that you can understand what it's doing and trust the outcomes. So this is an example here of, I picked this one because I'm Dutch, and we have one of the systems called Bonaparte, which is used not just in the Netherlands, but throughout the world in the context of, for example, identifying victims of disasters. And this is part of the MH17, which was shot down above the Ukraine in 2014 with like 200 Dutch people aboard and a lot of Australians. And they used this system to try and identify all the parts of the people they found based upon information about from their relatives. So that's many parts that they had to identify where they had DNA samples and that had to be processed and compared to relatives. So that's what this system is about. Well, this is more, well, I think we saw a cleaning robot moving around outside here. That's rather a safe place still inside the building. These self-driving cars, that's more scary out in traffic. So they've got lots and lots of sensors, which means a lot of sensor input, but a lot of uncertainty around that too. So we need to be able to predict and what will happen, and if there's other traffic coming up. Probably the cleaning robot, people just move around it, so it's not just an issue of can it detect people and move around them. But in traffic, that's a larger problem. So can we predict what's going on and act on that and try to avoid collisions and things like that? But of course, all the sensory input is not completely reliable, so we've got a lot of uncertainty there. Another example, maybe you've played around with these. Has anyone used this? This is Google's Imagen or Imagine. I'm not sure what the correct pronunciation is. I hope it's Imagine. Anyone who played around with this? Yeah, some? Were you impressed? Yeah. Anyone who played around with one of the other things like Midjourney or DALL-E, OpenAI? Yeah, or more of that. Okay. ChatGPT 2, I guess, which is similar, but not for images. So you just give a description of what you want, and it generates an image right here. And that's also something, so generating new things from things you've learned. So it has never learned this image, and still it can create it based upon the stuff that it has learned. This is an image, I'm actually, the previous years, this part of the summer school was presented by Antonio Salmeron from Spain. He donated a lot of his material to me, and that's why I also wanted to keep in this picture, because this is where he is from, Andalusia. And this is an image about detecting how land is used from satellite data, and then especially where the areas are protected, you want to make sure that nothing is going on there that shouldn't be going on. But that satellite data doesn't cover everything, so still you have to basically fill in the gaps there and predict what kind of land usage you have in the parts that you don't have the data about. Okay, so what we get from all these previous examples is that we're looking at applications that are built for situations where we have a large amount of data, but also a lot of uncertainty. Right? You can have data about a lot of things, but still there's a lot of information that you don't have, that you don't see, a lot of scenarios that are never covered or hardly covered. So that means that in all these domains you have a lot of uncertainty. And in that case, what you can typically do is use a probabilistic model to capture the uncertainty in a natural way, and then use algorithms, inference algorithms, to do the predictions and perhaps classifications built on that and stuff like that. Another thing about using these probabilistic models, as we will see, is that it also gives you an idea of how variables are related to each other, what things are dependent or independent. And we can also visualize that and give a good idea of how the domain, as far as you've modeled it, is structured. So because we're building on probability theory, that gives us a nice foundation under the models we're doing here in the associated math. And in that sense, we also have a natural way of dealing with missing data, because we can basically predict the things that we are missing from the things that we do know. And missing data, I mean, it could be, let's say, your data set with some holes in it, but it could also be completely missing variables and stuff like that. And one of the important things is the interpretability. That's the difference between the black box things and the probabilistic models. Okay. Well, if we're talking about uncertainty, we don't like uncertainty, really. We work with uncertainty, but humans don't really like uncertainty, so we try to get rid of uncertainty as much as possible. So then it's important to know that you cannot get rid of all the uncertainty that is around, because some things there's just uncertainty. For example, from natural processes, there's some randomness in things. So we often distinguish between two types of uncertainty. So the first is the aleatoric uncertainty, which is basically due to pure randomness. Right, so you've got, well, let's look at the example below in green. So we've got two variables, x and y. We want to predict y from x. And so what we do first is we estimate, so suppose we have the data, we estimate a joint distribution over the two. And we're going to use that joint distribution to predict y from x. So we can do that using, well, here it's the definition of a conditional probability. So we've got the joint, and we divide out the probability of x. So suppose y is the variable y models the growth of yeast, and x is the temperature at which the yeast is exposed. So at some stage we can observe the temperature. It's like outside, what is it? It's getting near 20 degrees right now, I guess. So I say, okay, it's 20 degrees. What is your prediction for yeast growth right now? So what kind of answer do I get from this model? So suppose I know the model. So I've got the conditional probability. I can compute that because I've got the joint. What kind of answer do I get? Temperature is 20. What is the yeast growth? So you can't give me a number or anything, but so what kind of an answer do you get? Can you speak up a bit? Some sort of average? Okay, so you're looking for a number. Yeah, you want a number. Okay. Any other suggestions? Yeah. A distribution. Yeah. Samples. Okay. So I get different kinds of answers here. Of course, depending on the application and the kind of result you want, you can take whatever you get from the model and change that into the answer you want. But the first thing you get is, in this case, a distribution, right? I've got the model here, I've got the joint, so I can just compute the distribution over y given x. So I've got a distribution, and then I can take an average or a mean or a mode or whatever from that, also depending on the type of distribution we have. But in essence, what we have is a distribution over y. We always have a distribution over y, so that means the uncertainty, even though I have a very specific, exact observation, still there's uncertainty in my answer. And that's a kind of uncertainty we call the aleatoric So even though I have my model, I have an exact observation, there's still uncertainty in the result in terms of having a distribution over the possible outcomes. So that's aleatoric uncertainty. If we look at estimating the joint, then we could say, well, the more data we have, the better the joint will be, the more reliable the joint will be. So there's epistemic uncertainty that we can try to get rid of as much as possible by having more data. So that means the epistemic uncertainty is something we can reduce by having more data, but the aleatoric ones is going to be there always. So we call that also irreducible uncertainty. And that's something very important to keep in mind. If you could spend a lot of effort in trying to get rid of uncertainty that you won't be able to get rid of. So you don't want to spend your effort there. Okay. Here's another example. As I said, you can, if you want to reduce epistemic uncertainty, you can try to get more and more data. Another thing is trying to see if you're perhaps trying to have a model that is too simple to do what you're asking. So what I have here is, if you look at the left image, you see green crosses and red dots. So suppose those are two possible outcomes. And you see that I've got one feature, x1. And those two possible outcomes, I can never separate the two in an easy way, because there's a region where I have both red dots and green crosses. So whenever I'm in that region, I'm just not sure about which of the two I'm looking at. So any point in that region could either be a green cross or a red dot. No matter how much data I will try to get to reduce my uncertainty, there is this region where I'm not sure if it's going to be a green cross or a red dot. And in this case, that is due to the fact that there's actually another feature. That is, and if I have the combination of the two, then I can distinguish between. So of course, the example was generated the other way around. So I've got two features, and I just flatten them and project them on one axis. But you see here that if you take the two dimensions, the two features, and you look at the data, then there is a way of separating the two. So that is something, and it may look somewhat counterintuitive that you're making the model more complex, and usually it's like keep it as simple as possible. But in this case, increasing the complexity of the model actually is a better option probably than trying to gather more data. So this is also a way of reducing the uncertainty. Okay, so from the examples we've seen right now, so what do we need if we think about probabilistic models? We need, as I showed right now, basically we want to be able to operate in high-dimensional spaces and still be able to work with that. So we still need to be able to do inference and learning in such high-dimensional spaces. And if we think about probabilistic models, and now more specifically about what we call probabilistic graphical models, then they offer this, also in a structured way, in the sense that we can give a structured specification of such high-dimensional spaces, high-dimensional distributions, in terms of low-dimensional factors. And we'll see an example of that in a minute. And this means that we also have efficient algorithms to do inference and learning that take advantage of this structure, advantage of the fact that we can factorize a high-dimensional distribution into smaller low-dimensional distributions. And moreover, the probabilistic graphical models, as the word already says, allows for graphical interpretation of the domain of the model that you're building. And in that way, it gives you something that is interpretable by humans. Some even say that it's interpretable by people that have no or hardly any mathematical background. Well, we can discuss about whether that's really true, but it at least gives you a sense of what's going on. Okay, so just to give you a very small example, and this is one of the examples that is typically also used in bachelor courses where you see some probabilistic graphical models, especially the discrete ones, and we usually call these Bayesian networks. How many of you have not seen Bayesian networks before? Good. So I think this is the easiest way to start with. So what we have here, so a Bayesian network is basically just a joint distribution over a set of random variables. And we can depict those and the relations between them using a directed acyclic graph. And we've got an example right here. We've got 5 variables and the relations between them in the graph. And we can model the joint distribution using these local conditional distributions, one for every variable, conditioned on the parents in the graph. Now, as I said, in this case, we're assuming all the variables are discrete. So you see these conditional probability tables with point estimates for all the variables, the values of the variables, conditioned on the values of the parents in the graph. Okay, so if you look at this graph, this gives you an idea of how the domain is structured. So is there anyone who would like to dare to explain what the graph is showing? Causal relations. So the burglary causes an alarm call causes John to call. Other suggestions, interpretations? We should be able to interpret the graph, right? So now I'm wondering what you're seeing. And forget about what you learned. So just tell me what you think you're seeing. So I've heard the causal relations.
I think it's just encoding the entire joint distribution of all the variables. Maybe if we could try to get any more interpreting.
Yeah, well, that's from the point of view, the technical point of view, right? So it's just a joint distribution, right? But we're claiming this to be interpretable, right? So you're basically saying we should not be trying to interpret this, but
I think it's very interpreted incorrectly.
It's very
Saying that it's causal is wrong.
Yeah. That it's causal is not necessarily wrong, because it could be very well causal, but it not necessarily is. Yes, and that's one of the things where I say we claim these things to be interpretable, even for people without a mathematical background, but it's so easy to interpret these things as causal relations. And if they're causal, they can be causal, but they are not necessarily so. Basically, they only are, we use the graph, the directed graph, as a language to code probabilistic independences. So there's a mathematical interpretation to the graph structure, whereas if we just look at it as a human, it's like probably causal, especially because the arcs are directed, right? And I think that in this case you could interpret these as causal relations. But what, for example, would happen if I change the direction of the arc between the burglary and the alarm? Would you interpret the graph differently? Or would you say, now it's wrong? Is it different?
Without any domain knowledge, we cannot say if it's right or wrong. So possibly it could be also the other way around.
Okay, and what if I said that at least the way it's modeled here, this is, according to the domain, this is correct. So can I make any changes to this without really changing the meaning of the model? So I can interpret all the arcs causally right now. Can I change the direction of any of these and still represent the same thing?
Can you define what the meaning of the model?
I'll get back to that. In this case, so I just want to have you think about this right now. In this case, actually, this is, if I start switching directions of arcs, I'm really changing the interpretation of the model. But that's not always the case. Just as that these happen to be causal or can be interpreted as causal relations, but they are not necessarily so. So keep those two things in mind, and I'll get back to this one and ask the question again. Because what it's really representing, the graph, as I said, it is a way, you could see it as a language. So we're using the directed graphical model, the directed graph, as a language to code probabilistic independences. And the way we do that is basically using these three building blocks. So the first one, where we have a serial connection, it basically says that information can pass from A to C unless I know something about B. If I know something about B, it is blocking the flow of information. And in a divergent connection, we basically see the same thing. So information can flow from A to C and to all the other ones, unless we have information about B, and then B will be blocking the flow. So the red color is denoting that. If we have information, evidence for those variables, observations for those variables, then they block the flow of information along those chains. And the only exception is the convergent connection, or the head-to-head, where the heads of the arcs, the arrows, meet. In that case, the interpretation is the other way around. So information cannot go through, so you can think of it basically as a sort of a sink. Information just drops into the sink, unless I have evidence or an observation, in this case for node A, and then it can go back up again. So then it can pass through from B to C, C to E, etc. So having observations, most of the time they block the chain, unless it's a head-to-head or a convergent connection, and then it works the other way around. And actually, the last one is a little more complicated, because not only having evidence for A will open up such a chain, but also if we have evidence for a descendant, so a child or a child of a child, etc. Because that's more or less indirect evidence for that head-to-head node. So now let's go back to the example we had before. So what we see here, we have a head-to-head node in alarm. So that has a different interpretation than all the other chains we have, right? Because from burglary to John calls through alarm, that's a serial connection. From earthquake to Mary calls is also a serial connection. And between John and Mary calls, there's a diverging connection. So for the last three, if I hear the alarm going off, then it's going to block the flow of information from burglary to John and Mary calling, from earthquake to John and Mary calling, and also between John and Mary calling. But the top one is a different one. So if I see the burglar running into the neighbor's house, it doesn't tell me anything about the earthquake. Unless I hear the alarm going off. If I hear the alarm going off and I see the burglary, then I'm thinking, okay, then probably it's the burglar causing the alarm, and there's not also going an earthquake going on. So having this difference in interpretation between the converging connection and the other types of connection, let me get back to the question I asked before. What if I change the direction of one of the arcs here? Would that change the interpretation of the model? They would no longer be causal effects, but then again, we're not actually capturing causality, although lots of people still call these causal models. Can I change the direction of any of the arcs here?
Without changing the numbers.
If you want to still represent the same joint distribution, you would also have to change the numbers. So the question more is, if you're allowed to change the numbers, can you still represent the same joint distribution if you reverse one of the arcs? Yeah.
I mean, in terms of those three factors, you just presented there's no bigger factor to change.
Yeah. So, as I said, the thing to look out for is the head-to-head connections. Because if I change something there, if I remove one or create one, I'm changing the interpretations. And in this case, whatever arc I reverse, I'm either removing or creating a head-to-head connection that was not there yet. So in this case, I cannot do that without really changing the interpretation of the model. But often you can. And often you can even do that by changing the direction into the one against the causal interpretation. And then mathematically speaking, we still have the same model. But looking at it as a human, you would say, oh, this is wrong. Right? The arc is in the wrong direction. So in this case, I cannot do it any different than what we have here. Because we're either removing or creating a head-to-head connection which has a different interpretation. Okay, so just some few checks to see if you got the idea. Formally, this is known as the D-separation criterion. It's not always possible to exactly capture probabilistic independence in these structures, so we need a way to read that from the graph, and that is what we use D-separation for. So I guess most of you who have seen Bayesian networks have seen D-separation, is that right? Who has never heard of D-separation? Oh, still that's a lot, okay. Good, then we'll go through that. So as I said, D-separation is basically the concept which we use to read independences from the graph. And D-separation means that two variables are D-separated when all the chains between them are blocked in the way that we just discussed. So here, if we, for example, look at node E, and we have evidence on all the nodes that have the little e attached to them. So we're looking at node with capital E. And C, G, and H, and D, they have evidence, observations, so they can block or unblock chains. And what you see here is in the green banner is the flow of where the information can flow through the graph. And you can indeed see it going down through H. H is a head-to-head connection, but it now has evidence, and that's why it can go through. This just reminds me one other thing I wanted to say about, I said if you have evidence for alarm, that basically opens up the chain, and I said this also counts for descendants of such a head-to-head node. So just to give an example of that, if the phone goes and John calls, then oh boy, the alarm must be going off. And that has the same effect as directly observing the alarm. But in this case, we have evidence for H directly, so we can pass through that head-to-head connection go up. Those are all serial connections until we reach D, which is again a head-to-head connection, but it has evidence, so the information can go through. Okay? Are there any questions about this? Yeah.
What do you mean by evidence here?
What do I mean by?
Evidence. The evidence.
Oh, that we have an observation for it. So as I said in the example right here, if I know that John calls, then I have evidence or an observation for it. Or I know that the alarm is going off. So I know for sure what the value of the variable is. And then if you think in terms of probabilities, so you're actually interested in then doing predictions, for example, with conditional probabilities given what you've seen. Okay, here a slightly more complex graph with the question, are the variables A and G de-separated given the evidence? There are already some hints for you in the picture, but just have a look at it. And who thinks they are de-separated? Got a few hands. Maybe you need some more time, but who thinks they're not de-separated? Some? Okay. Well, as I said, there are already some hints in here. The red bars, or they almost look like pieces of tape, are actually indicated that that is where a chain is blocked. So going from A down to D, I cannot go take the chain above through B because B has evidence, so that is blocked. I can go all the way down. I can go through K because I have evidence for a descendant. So that chain is opened up. But then L is a head-to-head node without evidence, so that is blocked. But I can go up. Then I have all serial connections until I reach J. And then I cannot go up to G because I'm coming from F through a head-to-head connection. And this head-to-head connection does not have an observation, nor does it have a descendant with an observation. So it's blocked, so I cannot go up from J to G. So in this example, with these observations, A and G are de-separated. Okay. Now the nice thing is that the way we define the model and the way we read independences or code independences in the graph actually describes the factorization of the joint distribution in all those local distributions that we define for every node given their parents. So the joint distribution factorizes exactly according to those local distributions. And that means whether you have the factorization, if you have the factorization, you know what the graph looks like. And if you have the graph, you know what the factorization looks like. And what you see here is an example of the joint distribution over all these variables right here, and the factorization into local distributions. And this also shows you that it's really easy to extend these kinds of models. Because if I add some nodes here, so I've added a variable season, cigarettes, another sensor that can detect smoke. This is a model about forest fires and trying to predict them from seeing smoke and the temperature. We've got different sensors for the temperature, and I've added a second sensor for the smoke. We have some information about season, which is something we know which season it is. It could be that someone dropped a cigarette, but that's not something we may directly observe. But we can just add those variables, and we only have to make local changes to the distributions. So we've added season, so we need a distribution or local distribution for that. we need to change the distribution for temperature because it should include season. We add something for cigarette and change the distribution for smoke. We have to update that. And we also have to add one for the second smoke sensor given smoke. So everything that is in red is new or needs to be adapted if we add pieces to the model. So this is a way that shows you that it's really a modular approach that you can, because we have all these local distributions, that you can easily extend these models to more complex ones. Okay. Now, one very simple example is a naive Bayes. I'm sure you've all heard of naive Bayes. Has anyone ever built a naive Bayes classifier? So, yeah. Did you use this kind of probabilistic model? Or didn't you really know what you were using? It's like doing statistics, right? I've got a statistical package and I'm just using some test and it gives me an answer, and that's how a lot of things work. So then it's nice to know what you're actually doing. Yeah.
But it also works in causal direction, right?
And again, not necessarily. You can interpret it as a causal direction if it's, or I should say, if there's a causal relation and you draw the arc in that direction, then you can interpret it as a causal relation. But again, it not necessarily is.
I mean, if we just do prediction, we just care about predictive power.
You don't care about. Well, the point is that with naive Bayes, that actually we're making if we forget about causality for a minute, but if you look at what the graph represents in terms of independences, you should now more or less be able to do so. So is there anyone who wants to tell me what the independences are that are modeled by naive Bayes, or the independence assumptions? Yeah? Oh, yeah. Yeah, so once we condition on y, so if we put an observation on y, then all the x's are independent. So you say all the features are independent given, if you use naive Bayes for classification, all the features are independent given the class node. And this is an assumption that rarely holds in practice, but it's such a simple model that we often use it anyway. Right, so we know that the underlying assumption is not realistic, but often it works good enough in practice. And then at least we know explicitly that we're making an assumption that is not valid. And as long as for the application that's good enough, you could say, well, I know what it's doing, and for my application this is good enough. So let's be practical about that. So in that sense, whether you are capturing the right independences and whether or not these relations are causal and can be interpreted causal, it depends on the application and whether or not that matters. And if it's good enough, then typically we just accept that we're not modeling the independences that actually hold in the domain. And here you see why this is a very popular model, because we get a very simple factorization just using, if we look at y given, so that is how we would typically use it to predict y given the features. And if you just use Bayes' rule, then you see that actually the distribution you want to predict is proportional to the joint. And that factorizes over all the separate features. I've seen an example once where a naive Bayes was used for a medical application to predict whether patients would contract pneumonia in an ICU unit. So they used a naive Bayes model for that. And one of the features was whether or not the patient was on mechanical ventilation. And there comes the problem of causality. Because if you interpret that as a causal direction, then you have pneumonia. Why? Causing mechanical ventilation. And in that case, the domain experts, physicians, said that model is wrong. Because pneumonia doesn't cause mechanical ventilation causes pneumonia. So could in that case I just cave into the domain expert and say, okay, then I'll just swap the direction of the arc. I'll just change. So suppose x1 is mechanical ventilation. I'll just change the direction of the arc from mechanical ventilation to pneumonia. Can I do that without changing the interpretation of the model? Now you have to answer the question. Okay, is anyone? Yeah? Yeah, so if I change only one, so we now have all the divergent connections, right? And they behave the same as the serial connection. So if I change the direction from x1 to y, then I'm adding a serial connection where all the other ones are still diverging. I'm not creating a head-to-head connection. I'm not removing a head-to-head connection. So I can still have the same, I have to change some numbers, but I can still represent the same distribution. So in that case, I could, say to the domain expert, yeah, you're right, I'll change the direction of the arc. But that is something I like this anecdote because it really shows you how strong this idea of causality is in the mind of human experts. And if you show them the model where the arcs are against the causal direction, even though mathematically it would not make a difference, it will make a difference in whether or not your model is accepted. Okay, just to give you, so that was a very small, simple example. This is a more complex example. This is a model about predicting classical swine fever, which is hard to predict because it's something that resembles very regular diseases in pigs, like colds and regular flu for a long time, except this is extremely contagious and lethal. So you need to predict this in a very early stage. And this is a model that was completely built by hand with domain experts. So there was some data, but the data is mostly taken from farms in cases there was no classical swine fever. So we have data in the case of no classical swine fever, but hardly any data of the case where there was classical swine fever. So this was completely constructed by hand. And you see there are a lot of variables in there that you could observe or measure in a pig. You've got the classical swine fever, the CSF diagnostic nodes somewhere on top. And we also have a lot of intermediate nodes that, if you think in terms of things you can observe, are actually hidden or latent variables because you cannot directly observe them in the pig. It's going on in the pig's body. So you can construct these real complex models. And, well, as I said, these were constructed by hand. Okay, so I have a little exercise for you right now. Who has never heard of the Monty Hall problem? Good. Who has already modeled a Monty Hall problem? I see some. Okay. If you already know how to do that, fine. Maybe you can help others. You can find answers to this on the internet, of course. Don't do that. Try to do the exercise. And the nice thing about this problem is that it seems really, really simple, but there's been an ongoing discussion, even among statisticians, about what the right answer should be. So I'm actually curious to see if you all come up with the same solution. The problem of the Monty Hall is it was a game show. I don't know how long ago. But you had these types of game shows, at least when I was a kid, on the television, and then there was nothing else to watch, so this is what you watched, right? And so the game show here, there's a contestant, there are 3 doors, and behind the 3 doors there are prizes, but there's only one real prize, so like a car, but you can also think of something more sustainable if you like. And 2 of the doors have, let's say fake prizes. If you look on the internet, you find a lot of images. There are always goats behind the other doors. I'm not sure if that was really the case, but again, you can think of something more animal-friendly or sustainable there. And the question was, okay, you've got the 3 doors, pick a door. So you as a contestant, you pick a door, and you say, okay, I want the prize that's behind the door. And then the host, who was called Monty Hall, that's why the problem is called this, the host would open up one of the 2 doors that you did not pick and show you, look, there's this fake prize behind it. And then ask, do you want to switch doors? Right, there's still this 3rd door that I haven't opened. You can pick that if you want, now that you've seen the fake prize behind the 2nd one. So the question is, do you switch? Would you switch? Okay. Or would you switch? Who would switch? Oh, you're not very convinced of your first choice. Okay. There's a piece of Python code on the GitHub where you can build this small model with the 3 variables. So there's most of the code is already there for you. And the idea is that you complete the graph by adding the arcs and the probabilities and see if you should switch or maybe have reasons not to. There should be TAs around here to help you. You can run the code in Colab. Is there anyone who needs more instruction for that? Okay, I'd like to move on. I've heard a lot of discussions going on, and I think most of you have not completely filled in the Python, but that's not such a big problem. At least you got started, and you also got started with a lot of discussions. And does anyone have an idea why this seemingly simple example has led to lots of discussions also among statisticians? I told the table up here, so they're not allowed to answer this. Were you having discussions? Because when I first asked who was going to switch, then everyone raised hands, basically. Do you still want to switch? Yes? Does everyone agree? Is there anyone who can come up with a reason when not to switch?
So if the host only sometimes opens the door, it depends on the rules of the game. So usually the rule is that the host always opens one of the doors, but if there's like, if that's not the case, and the host only opens the door like when you pick, correct?
Yeah. Indeed, I didn't tell you the rules of the game, and that was on purpose. The host always opens the door, but I think a lot of the a main reason why there's a lot of discussion about this is the assumptions, the other assumptions underlying this. And if you've basically picked this solution, so your choice of door affects the host's choice of door, and of course the price affects which door the host opens. There are a lot of assumptions underlying this. The first one is that the host knows where the price is. So he's not picking a completely random door. If the host doesn't know, how would that change this model?
But like, shouldn't it be implicit because the host doesn't know, they can randomly choose whichever, like the one with the price.
Yeah.
So the game doesn't make sense.
Yeah, but indeed, if you look from the perspective of the game, then you would think, okay, he probably knows because otherwise they destroy the game by opening up the door with the big price, and then you're not, well, maybe you're still allowed to switch, but yeah, it's an assumption for a lot of us which logical to make, but we should make it explicit because it really affects the model. Because if the host doesn't know, then the arc here between the price and the host is not there. And that means we might as well stick to our first choice and not switch. Because what we see right here is, well, some other examples. Probably most of you got the uniform distribution, if you got to that, on C and P. C is your choice, so perhaps you can just randomly pick a door. I'm not sure, maybe you have some preference, your favorite number or something. So that might not be a good representation, but it also assumes that the price is behind a random door. And you're not sure about that either. Because, it makes sense to just assume a uniform distribution, right? But again, that could affect the outcomes. But you see here, if you model it like this, if you do these assumptions, if you assume that the host knows which door the price contains and doesn't open the door, if you assume that the host randomly, if he has a choice, randomly chooses one of the other doors, instead of thinking, okay, every time someone is wearing black trousers, I'm opening door 2, if that's possible. I mean, the host could be playing a game of his own, right? So if you make all those assumptions, then this is probably the model you would end up with. And then you can do some computations. So you already have the priors on C and P. The whole model models a joint distribution. We can also compute a prior distribution over what the host is going to do by summing out C and P from the joint. And we can also compute, given the door I picked and the door opened by the host, how the distribution over the doors that contain the door that contains the price changes. And you see that if I know nothing at all, it indeed is, the price could be behind any door with the same probability. But if I pick door 1 and the host opens door 3, and I use the formula here, so basically the Bayes rule, then I can have the distribution over the doors, and in this case see that it's more likely that door 2 contains the price than the one I picked originally. So from that perspective, it looks wise to switch doors. But of course, you had a very good reason to choose door 1 because you believe the price is behind door 1, so you don't switch. But from a rational perspective, let's say, you should switch. Okay, so this also shows that when you're modeling, you may be making a lot of assumptions that you're not making explicit. Make them explicit. Okay, so back to basically what we already said before. We've got these probabilistic graphical models. I've showed you a Bayesian network with discrete variables. For those of you struggling with filling in the conditional probability tables in Python, Python is not the easiest to use for these discrete models. And there are other packages which are basically more convenient to do that. But now the rest of the course you'll be working with these kind of notebooks, not with the discrete models, so don't worry, that will be easier. Okay, so we've got a way of graphically depicting the relations between the models, the variables in the domain, even high-dimensional spaces. And we can do efficient inference and learning, taking advantage of the structure. We've shown that we have a structure that is somewhat interpretable, especially if you know what the structure means. But we haven't, I've mentioned the efficient inference and learning for a couple of times, but we haven't really looked into that, so that's where we're moving on right now. Before doing so, what we're going to talk about is, a lot, is parameters of a model. And if we think about discrete Bayesian networks, then basically all the probabilities in the conditional probability tables, these are parameters of your discrete distribution. So we often use theta for parameters. So basically these are all the parameters associated with the distributions over these variables. So you can see that you can have multiple parameters per distribution. In this case, for the discrete ones, I left out all the complements, the ones that sum to 1. So the idea is every variable has a distribution, and those distributions have parameters. And when we're talking right now about learning probabilistic models, it's not about learning the structure. You can do that. But what we're now talking and focusing on is learning these parameters. Okay, so learning. What is learning? At some stage, it was necessary to define what machine learning was. Nowadays, everyone talks about machine learning, but let's pick one of the early definitions to see if what we're doing is actually something you could call learning according to that definition. So this is a definition from '97, Tom Mitchell, who says that a computer program, or a model or an implementation or whatever you want to call it, learns from experience. And often experience is data, but also if you think about reinforcement learning, we still call that experiences. With respect to some class of task or one specific task, and a performance measure, because we have to measure if a model is doing okay. If the performance on the task becomes better in terms of our performance measure with experience. So keep those couple of ingredients in mind. And let's look at very simple linear regression. A lot of machine learning papers are actually doing just linear regression. Years ago, we would just call this statistics. But now it's called machine learning. Okay, so what we have is data about two variables. Let's look at a very simple case, x and y. And we want to predict y from x. And we're just fitting or assuming a linear relation between the two. Right, so we've got y is a plus b times x. And a and b in this case are the parameters of our model. So the slope and the intersect are the things we want to establish from the data that we have, and we assume we have labeled data, so we both know x and y. Let's take as a performance measure the root mean square error. So we just take the difference between what the model says, the right y is for a certain x, compared to what the true value is. And we just sum the squared differences just to make sure that the negative and the positive ones don't even out. And average that. Take the root to be back in the same unit of measurement. Okay, so the y with the hat is the estimate according to the model, and the y without the hat is the actual data we have. So if we're fitting such a model to data, then we were, let's say, learning A and B to get an optimal fit. So is that machine learning? Is that machine learning according to the model to the definition we've seen? Well, again, I've got a small piece of code for you. This time you don't have to write any code yourself. This is more or less a demo, but I thought it was nicer if you go through it yourself than if I do it. So please use that piece. There are also questions in there for you to think about, and then once you've gone through it, I would like to know whether you think this is machine learning or not. Let's take, well, you now know how to get it from GitHub into Colab, so let's take only 5 minutes for this. Okay, so I hear a lot of nice discussions going on. I would now like to get back here. So is this machine learning? Yes, I hear a very definite yes. Is there anyone who has doubts about that? I hear.
It's not a little biased to get kind of example because I cannot really see value of the straight line by picking up 2 points like at the beginning and the end.
Yeah, so well, you especially see, at least I saw some very nice ones. If you take very little data, you could, the red line is usually far off from all the other ones. And if it's not generate new data, and you see that. So is this machine learning? Yeah, well, nowadays we do call this machine learning with the idea that experience, that is just the amount of data we have. So the more data we have, we see that the root mean square error is going down most of the time. You see it sometimes spikes up again locally. But you could say that in the long run, the more data you have, the better fit you get, and therefore you're learning from experience by improving your performance measure. But we're not doing anything probabilistic here, right? We use a distribution to generate the data from for fitting the model. But the model itself, there's nothing probabilistic about that. But we can turn it into a probabilistic model, as we will see later on. Okay, so when we do want to learn probabilistic models from data, let's start very, very simple and just say, okay, I've got one random variable. Of course, I can have many, many, many more, but let's just stick to one for now. And what I have is I have a probability density function or a probability mass function, depending on whether I'm working with discrete or continuous variables associated with that. And I assume that I know the kind of model I'm using there. So I know the type of distribution I'm using. And what I want to learn is the parameter or parameters of this distribution. So you could say, okay, I'm assuming that I have a Gaussian distribution here, so X has a Gaussian distribution, and then my parameters would be the mean and variance or mean and standard deviation. And those are the things I like to learn. And so what do we have? As I said, we're assuming that we know the model. So that's an assumption we make. We're not learning the type of distribution we need. We're assuming we know the type or the family of the distribution. And just the parameters are the unknowns. So we have the notation here to indicate that. You could say it's conditional on the parameters. And an important thing to have here is the likelihood function. So the likelihood function, as you see in the middle here, it's basically just a probability of observing a series of observations for your X, so a sequence of samples, given some assumption about your parameters. We're assuming these are all independent, so we just simply have the product of the probability of each such observation given the parameters. And to make explicit that actually the parameters are the unknown things here that we want to focus on, we often write it in the form of, we call this a likelihood function, but we also often write it like this with an L or something, where it looks like the parameters conditioned on the data. But you have to remember that every time you read that you're actually looking at the probability of the observations, the probability of the data. So we've got the likelihood function, which is an important concept. And basically that gives us information about the parameters that we want to learn. So let's first look at, let's say, the classical frequentistic approach. And we're thinking here just a simple example of tossing a coin. And the coin has a probability of P of landing on heads. I've used a little graphical model picture to depict what we're thinking about. So we've got one random variable, and it has one parameter, which is the probability of heads. Now, for a frequentistic approach, right, probability is the relative frequency in the long run. So I first have to do a lot of experiments. So I have to flip the coin 100 times or something. And then I just look at, okay, how many heads, how many tails, and then I have an estimate of what the probability of heads is. So you can see here such a trial. So we've got one sample, which is a large number of trials, and from that we estimate the parameter. And we can do that, for example, using the likelihood function. So what we have here, so we're flipping the coin, and we've got, let's say, and we've done an experiment where we flip the coin 50 times. So we've got a binomial distribution here, and you see the formula up there. So that's the probability of seeing X number of heads in those 50 trials if the probability of heads is P. And it's the P we're now interested in. So I can graph the likelihood function for a number of coin tosses that we see here. So for 5 tosses or 10 or 25, 35. And these are the different likelihood functions. So what we have on the x-axis here is P going from 0 to 1, because that's the probability it could have. And so if I have those graphs, how do I estimate the parameter? So I have the likelihood function, and then what? Maximizing. Yeah, so in this case, just taking the mode. And, well, that would give you what you expect, right? So if you look at the 25 tosses, then the maximum value is almost at 0.5. So if it's a fair coin, that's what you would expect. Okay, so that's what you could do after you flip the coin 50 times. And the drawback is if you want to use this kind of thing to construct a probabilistic model, you want to be able to construct models for things you don't have to do 50 or 100 or 10,000 times before you can actually completely specify your model, right? So we want to be able to give estimates, and we as humans are I mean, if I ask you what's the probability if I toss this coin that it lands heads, then most of you will probably say it's a half. Maybe some of you will say, I don't know, because it may be biased. But I think most of you will say it's probably heads. So we want to give that, unless you start tossing the coin and showing me that it ends up tails way too many times, until then I'm going to believe that it's a fair coin and that any outcome is equally likely. And basically that idea is also what we want to be able to do in our probabilistic models. And that means we have to use a Bayesian approach. And to do so, what we're saying, okay, these parameters, they're not fixed quantities. Well, they are, but as long as I don't know what they are, I'm just going to assume they are random variables with a distribution. Right? So I'm not telling you the probability of heads is a half. I'm telling you, okay, as long as I don't know more, I'm assuming a uniform distribution where each of the outcomes is equally likely. So I'm actually treating the parameter as a random variable. And that means I can put a distribution on there even if I have not observed any data. If I haven't done the coin flips, I can still put a distribution up there. And how is this useful? Well, remember the example with the Monty Hall. If I enter my choice, Monty's choice, I do inference, and I get a new prediction for the distribution about which door contains the price. So I update my beliefs about which door contains the price. But I now can treat the parameter the same way, because it's also a random variable, as something I don't know, but I can make predictions about given the things that I do observe. Right? So now my parameter has become a random variable. I cannot observe it, but I can make predictions about it. So if you look at the graph here, and I now also notice there are differences in color. So the gray nodes are the ones I can actually have observations for, my data. And the white ones are the ones that are hidden, unknown. I cannot directly observe them. And I have distributions over them, prior distributions. Those distributions have parameters. And at some stage, I can assume these are fixed. So in this case, Q is assumed to be a fixed quantity. But if I want, I can change that into a random variable as well, et cetera, et cetera. So I can make this as complex as I want. But the idea is now, if I have X, if I assume a prior distribution on theta, I can just do inference to predict, given a new observation for X, an updated distribution for theta. And that's how I can learn an unknown parameter, or at least a distribution over an unknown parameter. But that means I have to start with a prior distribution, pick one, and then update it using standard inference to compute posterior distributions over my parameters. And those will be used as basically my parameter estimates. So this shows you that actually inference and learning from a Bayesian perspective, is the same thing. And that is more or less reflected also in this list of terminology. So when we looked at the Monty Hall problem, I said, okay, we've now got a joint distribution over those 3 variables, and I can compute prior distributions for each of the variables, and a posterior distribution that tells me what the probability is that the price is behind a certain door, given the choices of myself and Monty. But now when we're looking about learning from data, usually the terms prior and posterior and joint are reserved for the components that include the parameters. So when you're talking about priors and posteriors, it's also, you always have to figure, okay, are we in a context of learning, or are we in a context where we have a model and we're just using it for prediction? And that's also, so we've reserved the F for the distributions over the observable variables. And whenever we include the parameters, you see a different notation. So the pi here is used as a prior distribution. We've got the joint over the observable variables and the unknown parameters, the hidden variables. And the posterior distribution is the posterior over the unknown parameters, given the data that we see. And of course, you can just, if you have the joint, you can compute that from the joint. Prior predictive distribution means is comparable to the prior we had before, so it's just a distribution over the data. So we integrate out the unknown parameters or sum them out in case we have discrete distributions. And we have the posterior predictive distribution, which basically is the prediction of what is the next data point we expect to find given the data we've seen up till now. And then we, again, condition on the parameters and sum them out or integrate them out again. So what you have basically is here that you need the likelihood for the next data point, and you need an updated prior, so the posterior for your parameters. The last two, so the prior predictive and the posterior predictive distribution, or usually posterior is left out, those are the two you actually use for validation. So once you've learned your model, and you have new data coming in, you can see if it shows the same kind of patterns or behavior as you would expect from the model. Okay, so let's again look at a very simple example. I'm still tossing coins here, but now I'm not first tossing 50 coins and doing an estimate, but I'm now tossing coins one at a time, or tossing one coin multiple times. But every time I toss the coin, I take a separate variable here to represent the outcome of the coin toss. So that's the nx variables here. So they all have a Bernoulli distribution. Because it's one coin, they all have the same probability of heads. So they share that parameter. That's what you see in the picture. I also put the ones and the zeros, the parameters of the distributions we have. So I start by assuming that P is a uniform distribution. So the probability of heads is anywhere between 0 and 1. Usually those zeros and ones or constants are left out of the picture, but here I just put them in just to make it explicit. So if this is the model, and P is the parameter we want to learn, we start with a prior distribution over it. I'm assuming it's uniform. Is that a realistic assumption? No? Yeah, so you say it's better to start with something that has a high mass on 0.5. Well, yeah, you could do that. We'll just stick with uniform for now. And I'm doing that just to show you that it doesn't really matter. Okay, so the first things we need is the likelihood and the prior. So the likelihood is the probability of seeing these n results given our parameters. So that's just the probability density function here. The outcomes, so it's the number of heads we're looking at. So every toss we either get 0 or 1 heads. So that's why the xi are 0 and 1. P, of course, is any number between 0 and 1. So that's the formula we have. P to the times the number of heads we get times 1 minus p to the number of tails. That's the probability of observing that sequence. The prior is 1, right? 1 over just the length of the interval. So these are the two important ingredients that we can now use. So we've got the prior, we've got the likelihood, and we can use those to compute the posterior over P. Okay, so you take the posterior, that's just the form we had before. So you see the likelihood times the prior, which gives us the joint up there. And we divide by, so this basically just Bayes' rule we're doing there, right? So we have to divide by the probability of the data we've seen, so sum out or integrate out the parameter. And then we end up with the expression right here. Now, the nasty thing about the expression right here is the denominator. We see an integral there. We don't like them. We don't want to compute them if we don't have to. So a lot of approaches, basically, a lot of the issues that we need to deal with in learning have to do with, okay, what do we do with this integral right here? And sometimes we can solve this analytically, and not even by really computing the integral, but being a bit more smart about that. And that is by doing some pattern matching. And in this case, if we take the beta distribution, which has two parameters, alpha and beta, so the formula is up there. In front, we have a gamma function, not a gamma distribution, but a gamma function. So the gamma of n is n minus 1 factorial. And if you look at that, then apart from the whole gamma part, the p to the power something times 1 minus p to the power something looks very much like the expression we had. So let's see if we can match the two. So we had that expression, so what we see above there, that's just the denominator of the fraction we just saw. So we match alpha to the sum over the number of heads, and beta or alpha minus 1 to the number of heads, and beta minus 1 to basically the number of tails. And if we fill in that, then we get the latter part of the expression right here, right? Because we have to fill in alpha and beta in the gamma part. But now we have an expression, this fraction of gammas, that wasn't in there originally. So we just divide it out again. Right, so the first part here is just 1 over the second part. Yeah? And then the nice thing is that the whole gamma part is a constant, so we can move it out of the integral, and then what's behind the integral is just a probability function for the beta distribution. And if we take the integral, so we compute the surface beneath it, it should be 1. So now the whole integral is gone, because we can replace it with 1. So I'm only left with this gamma function, and as I said, that's just a factorial. So I now reduced analytically something that looked hard into something that is actually quite simple to compute. So what we now did was the integral there in the fraction. So this is just a slide we had before. We now established that that is just equal to some fraction of the gamma functions. That was the thing below. We still have the thing in the upper part there with the p to the power something. So the result is the one in the line there. And that expression, if you again take the beta function, is just a beta function with these two parameters. So that means that our posterior distribution is just a beta distribution for which we now know the parameters. So what we started with is a Bernoulli or binomial distribution for our likelihood. We had a uniform distribution for our prior, and actually the uniform distribution is a special case of a beta function. It's a beta function with parameters 1 and 1. So I've combined a Bernoulli or binomial likelihood with a beta prior and end up with a beta posterior. And we did this all analytically. So that's very nice because then it's easy to compute. And there are actually, as I said, that's easy to compute. There are actually more of these nice combinations. So what you see here is a list where the prior is from the same distribution as the posterior. If you combine them with the likelihoods we have here, and there's a whole list of these examples, you can see the top one where we have the Bernoulli prior with Bernoulli likelihood with a beta prior gives us a beta posterior. That's what we just saw. But you see a number of other combinations. A lot of times, for example, the Dirichlet prior, which is halfway through the list, is something you see often because, again, that is something that gives you this nice combination. Whenever you have this property, we call the prior and the likelihood conjugates. So these combinations are things where we can solve, basically analytically solve the problem. But we cannot always do that. Okay, we've seen the likelihood, we've seen the prior, we've seen the posterior. There were two other things, the prior predictive distribution and the posterior predictive distribution. So this is just to complete the picture. So if we compute the prior predictive distribution, which was basically just the joint over our data, what you see if you do the numbers, then you end up with a half. So the probability of the coin ending up heads is a half, according to the prior predictive distribution, even though I put a uniform prior on the probability of heads. Right? So it looked like a bad prior because it looked like we had more information. It would make more sense to pick a prior with more mass on a half using domain knowledge, but even the uniform prior gives us a good estimate here. And then we also have the posterior predictive distribution. As I said, that is for validating your model. So I've got these n observations. What is my prediction for the next coin toss? And I compute them again, given the formulas that we've shown before. And here again, with the integral, we use the trick that it resembles a beta distribution, and we try to rewrite it into one of those. And then you end up with an expression that contains only the gamma functions, and you notice that the parameter is no longer in there. Okay. Now, typically, so you can do the learning and the updating, and you get the distribution over your parameters. And doing it that way is called fully Bayesian. So we also compute the denominator, the integral there, which is the hard part. But sometimes you don't want to do that, or maybe you cannot do that. There are other ways to then get an estimate for your parameters. One is the MAP, the maximum a posteriori estimator, where you just take basically the combination that gives you the highest probability of the observations you've had. So that's the argmax there. You pick the value of the parameter that gives you the highest probability of your observations. And so that's basically just an optimization problem, and you see that we use a lot of log terms there because, well, if you use a log, you change all the multiplications and divisions into sums and minuses, and that's easier from a lot of perspectives. You could also just forget about, so you see the prior on the data still, on the parameters is still explicitly in there. You could also forget about that. And what you then get is what we call a maximum likelihood estimator. And then you're basically back to the frequentistic approach. But you can still do that even if you're using this. Okay. So what we see now is basically what we're going through is what is called the probabilistic modeling cycle, where we build a model using some kind of approaches. You can see first you assume some kind of probabilistic model. You see a number of suggestions up there. Then you infer the parameters or distributions over the parameters using all kinds of algorithms. Either do it in an exact way as we just saw, but if you cannot do that, there are lots of algorithms. One of the things there you see is Markov chain Monte Carlo and variational inference, and especially variational inference is something you will see more in the course. You criticize the model, so you want to know if it's doing any good. And if it's not, you can revise it and then try to learn a better one. And in the end, you apply. And so you can use many types of models, of course, but this is the model you hypothesize, basically. The one that you learn the parameters for, that is where we're using the PGMs, probabilistic graphical models. Okay. Now I just wanted to go through some simple examples to show you how to do the modeling, basically. So still just tossing a coin. So I have a random variable which represents the result of n coin tosses, still with p, the parameter probability of heads. So in this case, what are the random variables? Well, we at least have x, right? What are the fixed quantities? Well, let's start out by saying this standard situation. So we've got x, we've got an unknown parameter, theta, which is our probability of heads, p right there. In this case, we also got n is the number of coin tosses. So are there any hidden variables? If you want to take a frequentistic approach, then basically this is the model we're looking at. If you want to take a Bayesian approach, how do we change this? Yeah. Yeah, so the theta will be a variable, random variable. What about n? The number of coin tosses. Does that remain a fixed quantity, or do we want to change that into a random variable too? Yeah, let's keep that one fixed. Yeah. Okay. So we take theta to be a random variable, and it has a distribution, and it can again have parameters. Yeah.
I probably have a very stupid question. Why do we assume that our parameter theta, which we use further for like maximum likelihood estimation or posterior inference, that it enters the likelihood with this like this exact dependency with like 1 minus x to the power of theta times x. No, vice versa, like theta to the power of x, not theta multiplied by x. Because we have discrete outcome and continuous parameter, the parameter would enter, like you could have different functional relationships.
In this case, so we're referring explicitly to the coin tosses. So we're assuming that it's a binomial distribution or a Bernoulli distribution.
Like in Bernoulli distribution, we essentially only have probability table, right? And then we say, we can find a continuous function, how parameter defines this probability table, but this continuous function, like there are many of them. It's not only like the usual like that we have.
Yeah, but what you do is you're now saying, basically you're still saying, okay, I've got.
So if you can go a couple of slides back
Yeah.
to where you had the like.
This one.
The first formula.
Yeah.
If you say p times sum over xi plus 1 minus p times. So if you don't have power operation but multiplication and then sum, it's also going to be a function which yields like correct likelihood.
Yeah. So what you do here is.
I wonder if the inference would be different then.
Well, your formulas would be different. Of course, you can pick any likelihood you want, but what you do here is you're saying, okay, I'm assuming this is a Bernoulli distribution, and then I know that it looks like this. So this is what I get in the different formulas.
Because we can only observe, outcomes of experiments. We don't know what is the likelihood, like how reality can, what's the function in reality, right?
Yeah. So you're making a. Yeah. Well, that's basically what. You're assuming here, you're hypothesizing that this is the model that basically is the right one. So now I could say, okay, I know I'm doing coin tosses, so I know it has this distribution. And your point is that often you would not know what distribution you have, right?
Like mathematically, you don't have unique likelihood, right, for Bernoulli distribution.
Yeah, but what you do is you hypothesize one, and you go through the math, and then you can use your predictive distribution to see if you continue tossing the coin, if it behaves the way you want it to behave. And if it doesn't, you go back to your model. So you hypothesize a model, and you work from there. It can turn out that it's not the right model. Even if you've optimized your parameters, that it still doesn't perform the way you want it to. And then you just need another model.
Okay.
Yeah? Okay. So here we are. So we've got the coin toss. We've changed the parameter into a random variable, and let's say now, to make it a bit more interesting, we think the coin may be biased towards tails. Can we include something that indicates whether or not the coin is biased? And how would you do that? So let's say we just want to include a variable which says the coin is biased, yes or no. Where would you add this? At the top of the empty arrow. Yeah. You first, yeah. So yeah, and how would you basically go about encoding it in the prior?
For instance, we were talking about beta prior on, we can choose the parameters of the beta distribution such that it has more mass towards.
Okay, so you would already include it in the parameters. Other suggestions here? Same suggestions? Yeah. So for example, what I could do is add a random variable which just says it's biased or not towards tails. And then, of course, I could put a distribution on that which has a parameter of the actual probability that it is biased. And of course, as it shows, it's white. So I don't know. I cannot observe this directly. But I can explicitly model it. And now I have a sequence of unknown variables. But that doesn't matter. I can still do the same tricks and update them from the observations I have. But I do need to specify distributions. So in this case, the distribution over a parameter theta will depend on whether or not the coin is biased. And in that sense, it is included in theta's parameters, but now in a more explicit way. I could also do two coins, and both they have their own probability of heads, and both can be biased towards tails, and I can here assume that it's the same, that they share that variable. But if you don't agree with that assumption, you can model it in a different way. But at least the graph shows you that this is an assumption. So you can make these models as complex as you want and make basically everything you want to assume explicit, and you can do the same trick over and over again. But if you start to building very complex models, it becomes less easy to read them. So that's why we often use a plate notation just to summarize the repeated structures. So here, if we have capital N number of, in this case, variables that all share the same parameter, what we usually do is we just put that in a plate, in a box, and indicate how many of those we have. So here we have xi, which goes from 1 to n. And they all share the same parameter, so the parameter is outside the box. And that means you can represent quite difficult models, complex models, even in a quite compact way. So getting back to our logistic regression example, we said there's nothing really probabilistic about that. We can make a probabilistic interpretation of that by saying, okay, what we're predicting, y from x, we can just assume y is a random variable and have a distribution over y. So the underlying model is basically down here. So here, W0, W1, or the A and B we had before. We can also say, well, there's some noise there. I'm going to model explicitly in epsilon I. And then we have, in terms of plate notation, a model like this up here. So we have a distribution. Y is a random variable. It depends on W, so the slope and the intercept. I can start by assuming that it's a normal distribution. So we've got the mean and the variance up there. I can explicitly model the noise as a random variable, which takes on some distribution, for example, a normal distribution here with 1 over the precision parameter gamma. And actually in plate notation, it looks like this. If you would unfold it, of course you would get n of these y variables. But you can again see that the things they share and the things that they don't share explicitly. So anything in the box is repeated. Anything out the box is shared by all of the y's. Note here that x is not a random variable. So I don't have a joint distribution here over x and y. Anyone have an idea why not? Yeah, because then I would need an estimate of what kind of distribution my data has, whereas if I just want to predict y using linear regression, I don't need to do that. So here x is a fixed quantity and not a distribution. This means that I cannot generate, once I have the model, I cannot generate new samples. So this is not a generative model. So most of these, if you use them with these probabilistic graphical models, most of them can be used as generative models. That means we can generate data, new data once we have the model. So we have an entire joint distribution, which means we can also generate new data from them. And you compute, if you want to do prediction, you compute the conditional probability from the joint, but you actually learn the joint. You also have discriminative model, and that basically means you directly estimate the conditional probability. So you can do the prediction, but you cannot use it to generate new samples. You see that a lot of these probabilistic models actually build upon generating new samples from the things that they have learned. So then we're in the top, the green category. And the discriminative models are really used only for prediction. So you see the different types of models. So the things like logistic regression and neural nets typically are the discriminative models. And you look at Bayesian networks, except when you model a logistic regression as we just did, then we don't have a generative model. But usually Bayesian networks, probabilistic graphical models are generative models. And the nice thing is that they typically perform better with less data. So if you don't have a lot of data, you can get good performing models even with little data. Okay, so I just want to show you a number of often used models, and often used models that have latent variables more in general, so hidden variables which are not necessarily the parameters of different distributions. And one of these is the mixture of Gaussians. So anyone here who has worked with mixtures of Gaussians? A lot of things. And who knows what they're actually doing? Or is it again like, okay, I've got a statistics package here and I'm just selecting a test and then it gives me an answer. Okay, so let me try to see if we can build a more interpretable model that is showing you what these things are really doing. Okay, so the point is that these are often used for clustering. So I've got data, and I assume that is, for example, that it's generated from 3 Gaussians. And those are my 3 clusters. So again, you see some things that are most likely generated from, for example, the red Gaussian, a number of points that are most likely generated from the blue one. But you also see a lot of overlap, where it's hard to distinguish between the 3. So the colors indicate which ones they are actually generated by, but of course we don't know that because we don't know the actual underlying distributions that did that. So what we have is, how do we formulate this model? Well, we're assuming we've got k, so in this example, 3 Gaussians that have generated these points. So this is an assumption, right? We're just assuming we've got k Gaussians that have generated these points. With some frequencies. So the different Gaussians are more likely, one is more likely to generate points than the others. So those are the thetas right here. And we've got a number of observations. And so the x here in gray, these are the actual points we're seeing. And so what we're modeling here is, okay, every point was generated by a Gaussian distribution with its own mean and its own standard deviation. So those are the mu and the sigma we see here. Every Gaussian has one. So if we've got k Gaussians, we've got k means and standard deviations. So that you see they go from 1 to k. But we don't know which ones. But we can model or include a variable which says this point is from this Gaussian. And that's our z right there. So z tells us for every data point, it was generated by this Gaussian. So for every data point, we've got a z. So you see z included in the plate that goes from 1 to n. And of course, we don't know this, but we can model it. And if we know which data point or which distribution generated which data point, so if we know it's from the red distribution, then we know the mean and the variance that belongs to it. But we don't know, so that's why it's a hidden variable. And again, this is also given, we're assuming here it's a multinomial because every Gaussian has its own probability of generating the data, and those are exactly the thetas we saw before. So this is the model we get that describes this. Now, if we want to learn those parameters and we want to take a Bayesian approach, again, what we do, turn everything into a random variable. So the theta and the mean and the standard deviation, again, assume distributions that can have their own parameters, etc. Do the same trick all over again. So hopefully this gives you an idea of the things you have already been working with, but what they're actually doing. Okay, another very popular model is the factor analysis model. Anyone who's worked with those? Very few. Okay. You see a lot of this, for example, in social sciences experiments where you have these surveys of questions that people need to fill out, and they have to answer lots and lots of questions, but what they're actually looking for is measurements on a few underlying hidden dimensions. And the factor analysis is basically done to translate the large number of measurements into the smaller number of underlying factors. So you could also view this as sort of encoding mechanism. So the measurements or the answers to questions, whatever it's that you're looking at, those are the x's right there. So those are observable. The underlying hidden factors are the z's. And we're assuming that all of those are independent of each other. And you should now be able to read that from this graph, that is the assumption. Okay? And what we have here is a description of how the model works. So every measurement, so for example, for x1, is assumed to be a weighted combination of all those factors. So every factor contributes to some extent to the measurement x1, but there's also some variance in there that is not explained by these factors, so that's the theta at the end there. So you could interpret that as noise or whatever. So it's a weighted combination of all the factors plus some more. So that's for a single observation. So that's a single filled out survey with M answers to questions. Now, if we model that in a probabilistic model. So what we get, we've got, well, multiple observations because n people filled out these questionnaires. And again, we're looking at something similar that we saw with the mixture of Gaussians. So now we're looking at two different indices because I already have m variables for one single, let's say, subject who filled out a questionnaire. But then I have n different subjects filling out these questionnaires, so I have m times n different answers. So that's why I get the I and j indices right here. And we have that every factor contributes to every of the x's of every of the people. Now, I should say, for every factor, we have all the x's, and then for every person, we have a measurement like that. So we get a model like this, and again, we have the weights here, so we have every x is a weighted combination of the factors. So for every person, for every variable, we get a vector there, w. And we also have, so I have only one line here of the ones we had before. So for every x, we have one theta explaining the variance that is not already explained by the factors. So we also have that right there. And again, we can put, as you see here, on all the things that are unknown, we model them as hidden variables, random variables. They all have their own parameters, which are not shown in the graph explicitly right here, but you can imagine that they're there. And you see you can have a compact representation of quite a complex model with a lot of repetitions, which should give you some idea of how the underlying model works. And again, given the observations and all the distributions you hypothesize there, you can use your data to learn the unknowns. Okay. So as I said before, learning and inference in this context are actually the same because you're using inference to compute posteriors over your unknown variables. And the benefit of that is that we have a lot of algorithms for inference already there. So from the probabilistic graphical models, there are a number of algorithms that can do inference, and we can just use them in the context of learning as well. So what we're typically looking at is what we call a probabilistic graphical model, a Bayesian network, and we have evidence, so we have observations. So what we're interested in computing conditional probabilities of any variables of interest, xi, given our evidence or observations. And we have numerous inference methods to do that. And we typically distinguish between exact algorithms and approximate algorithms. For exact algorithms, you could do this brute force, right? Just compute the joint and then sum out or integrate out everything you don't need, which is typically not very efficient. So you can do that for small models, but then you quite fast reach the limits of what you can do. Or you can take advantage of the network structure or basically of the factorization of the fact that you have everything local. And then you can often do it efficiently. So if you can do it exactly, if you can do exact inference, then you do exact inference. If you go to large models, that's not often possible anymore. So then we have to use different techniques. And again, you can distinguish different ones, and the distinction you could make is between sampling algorithms and deterministic algorithms. What I want to show you first is a very simple exact inference algorithm, which just give you a flavor of what it does. and this is called variable elimination. So what we have here is a network over 5 variables, and we're interested in the probability distribution over x5 alone, so the prior distribution over x5. Again, I'm assuming everything is discrete here, so I have summations instead of integrals. So what I do is, well, I have the joint distribution over these 5 variables. I know it factorizes according to the graph structure, so you can check later on that this is the factorization that you get for this graph structure. And then I have to sum out x1, x2, x3, and x4 if I want to know the distribution over x5. So let's start by summing out x1 first. And that means I take all the terms that include x1, group them together, and put the summation over x1 in front. And that gives me something I call h right here. So I get a different kind of factor where I've already done some of the work there. And that means I've reduced the problem from with one variable, because now I only have to sum over 2, 3, and 4. So x1 is gone. Perhaps you can imagine that the order in which you do this summation may result in smaller or larger of these other factors that you create. Right, because here I still have a distribution over x2 and x3. So depending on the order I take, I can get smaller over distributions over or factors over smaller number of variables or larger number of variables. So I can, depending on the choice in which the order in which I do this summation, I could do it more efficiently or less efficiently. But it's not an easy problem to determine what an optimal way is of summing out. This is called an elimination order. So here's the code here. I'm going to skip that. But the point is that the intermediate factors that you create, the size of that is what is determining the complexity here, and that can differ a lot. So doing this and creating these projects of functions means that especially for discrete variables, that inference is exponential in the number of basically the variables you have, depending on how you pick an elimination order, but also how the graph is structured, how many parents nodes have, etc. So again, if you can do exact inference, it's nice to do that. If you use a closed form, it's nice to do that, because then you can do the summation and the products easily. But if you can't, you need to do approximate inference. Different types of, we've seen the Markov chain Monte Carlo mentioned before. Important sampling MCMC are kind of types of algorithms that are used for approximate inference. And the idea is that because they are sampling algorithms, so they basically take samples from the distributions you have, that every time you run them, you will get different results. Right? So every time you run an approximate algorithm based on sampling methods, you will get a different result. If you do it often enough, you will typically get accurate results. Deterministic approaches are different in the sense that you could say it's more or less exact inference, but we first take an approximation of our distribution with a function that is easier to handle. And then we do things in an exact way. And then it's deterministic in the sense that whenever you repeat inference, you're doing it on the same function and therefore getting the same results. But you are always getting an approximate result because you're starting with an approximated function in the first place. So you won't get in sampling you can get the correct result. And with the deterministic approaches, it depends on how good your original approximation was, how close you get to the truth. Okay. I think I'll skip the last a bit more about MCMC, doesn't matter that much, and go to my conclusions. So, probabilistic graphical models, probabilistic modeling is very nice because on the one hand it's grounded firmly in probability theory. On the other hand, especially being able to represent visually an idea of the underlying structure of the problem. Once you know how to read the graphs, you have an interpretable model that can help you get an idea of what you're actually doing and therefore also explain what the model is doing. And we've seen that inference and learning, although there are two different concepts, from a Bayesian point of view, what you're doing is actually exact the same. So if you can do inference, you can do learning. And we exploit the algorithms we already have for inference to use in learning. Do we do it exact if we can? And if scalability is important, we go to approximate inference. But the best thing about these probabilistic models is their interpretability. Okay, so with that, I would like to say thank you for your attention. I hope you learned a lot now and enough to proceed in the rest of the course. Also, again, a thank you to Antonio, who shared a lot of his material for this, and enjoy the rest of the week.